Alright, I want to work out another lever problem here. I'm going to draw this up for you guys to kind of get a good idea. So I'm going to kind of draw my wheelbarrow. Of course, we got our wheel here, and that comes out. We got the side parts. This, of course, is the tub that holds whatever we're lifting. So, and the handle here, and just most wheelbarrows have some piece of metal there as a rest point. So we'll draw this in. As I give it a little bit line, define a little bit. That's just kind of extra stuff. I don't have to do that. Of course, I drew this wrong here, so let's go back because in reality, of course, that comes down to the center. So we'll do that. So our wheel should be here at the center of the wheel for our wheelbarrow. Now, question is we've got a wheelbarrow used to lift a 400-pound load. So I got some rocks or gravel, dirt, something in here that's a load, and we know that that is 400 pounds. So that force is 400 pounds. So 400-pound load. Now, the length from the wheel axle to the center of the load is 4 feet. So right here, we're going to kind of draw the center right here. X marks the spot as the center, and that center to go from there to the center of the wheel axle is 4 feet long. That is E of something. So, as remember, and we'll talk about this after I get everything else, the length from the wheel and axle to the effort is 6 feet. So here we've got from the wheel and axle to the effort, which is down here, is 6 feet. Now that's good to notice what the effort was, because that tells us that this is the DE, our distance of our effort force, which means that we are going to have to apply an effort force going up here, which means this is we know that this is our resistance force because that's our load, and if this is our resistance force, then this is our resistance diameter of 4 feet here. So first thing you need to ask yourself, is this a first class, second class, or third class lever? Well, our fulcrum is here at the center of the wheel on this, which means we've got one force going down, the other force going up. The force is going down is in the middle. That means that this is a second class lever, because remember, we've got those 3 classes of lever. Let's talk about those for just a minute. A first class lever here, we've got a fulcrum that could move anywhere and be placed anywhere the length of the actual lever. Both forces are applied in the same direction, an effort force. We got a resistance force. We got a distance from the force to the fulcrum, resistance force here, and a force to distance to the fulcrum to the effort force, or DE. So there's the components of a first class lever. So that's first class. The second class lever, the fulcrum is actually you've got one force pushing one direction in the middle, going down, the other force going up, and of course we've got our distances to both of these as well. That is the second class lever. And then right down here, I will go ahead, the third class lever. The fulcrum is on the end as well, but here our forces change. The force pushing up is in the middle, so the force pushing down, so this is our effort force here, and our resistance force is up here. So now that's a little different again from the second class, where our resistance force was in the middle, and our effort force was on the end. So we keep tabs of which type of lever this is. This one is a second class lever, and I'm going to solve because I don't have all the information. I want to know how much effort force it's going to take me to lift this 400 pound of weight on here. Now I want you to stop and think for a second. Is that going to be more or less than as we go through for this? So should it be a greater amount of effort force on our part or a less amount of effort force? And ideally, when we're doing this, we want to try to decrease the amount of effort that we put into it. So hopefully that's going to be the way this works out. So, and we're going to again use our formula. We're going to assume static equilibrium. We're going to set our ideal mechanical advantage, our IMA, equal to the actual mechanical advantage. In this case, I already know that my actual mechanical advantage equals the force of the resistance over the force of the effort. So, and we are trying to find the force of the effort, which we don't know yet. So we got to find our ideal mechanical advantage first. Ideal mechanical advantage equals dE, the distance of our effort, over the distance of our resistance. So in this case, the distance of our effort is 6 feet. The distance of our resistance is 4 feet. So our unit of feet cancels out. 6 divided by 4 is 1.5, or we could say 1.5 to 1 is our ideal mechanical advantage. We have a ideal mechanical advantage of 1.5 to 1. Now, assuming, and going back to our assumption here of static equilibrium and setting IMA equal to AMA, all I need to do now is plug and chug back in. We've got IMA equals 1.5, so that's our IMA, and it equals AMA, which is our force of the resistance, which is 400 pounds, over the force of the effort, which we still don't know. And I'm getting that from this formula right here. AME equals free. AMA equals FR over FE. Alright, from this point it's just a matter of plugging and chugging for the algebra. So, force of the effort force equals 400 pounds divided by 1.5. Alright, so our effort force should be lighter here. So we take 400 divided by 1.5 and we get 266.667 pounds. So does that seem practical? Would I want to still lift 266 pounds on this wheelbarrow? That's still a lot of force there that I have to exert and put in there. So maybe we would improve if we wanted to make some improvements on this to get it a little bit better. What would we want to do? Maybe we lengthen the axle here. Let's see if it would be better if we actually took and did this by 8 feet. Let's make our wheelbarrow a little bit longer. So here, so in that case, my IMA equals 8 feet over 4 feet. Gives me a mechanical advantage of 2. So my, still the same weight, 2, going back here to my mechanical advantage of 2 equals 400 pounds over FE, the effort force. FE now, this is getting a little bit better. My FE in this case will equal 200 pounds. So that's getting a little bit better, but still, you know, I'm kind of not as young as I used to be. Got a little bit of pudge around the middle. That's still an awful lot of weight for me to exert, so I want to decrease that a little bit more. So here, now, I'm going to keep that 8 foot long wheelbarrow, but maybe I slide this resistance force. Let's move that down. I'm going to change that position of that load, and I'm only going to come out 2 feet here with my resistance distance as opposed to 4 feet. Now let's see how it changes. Now my IMA mechanical advantage here becomes 8 feet over 2 feet, or mechanical advantage of 4. And let's go ahead and see now that I got a mechanical advantage of 4. I still got a 400-pound load that I'm trying to lift, so that's over F of E. Here my FE actually ends up equaling 100 pounds. There you go. That's better. That's more reasonable. I can handle lifting 100 pounds a lot better than I can lifting 200 pounds or 266 pounds or even the 400-pound load that we originally put on here. So this is one of the ways, just by changing the links or redesigning some products, we can get and use the concept of mechanical advantage and a second-class lever to decrease the amount of effort that we have to put into one of these simple machines to achieve work as we go. So go ahead, watch this again a couple of times. If you're still not clear what I did, feel free to come into questions or shoot me an email, and I'll be glad to go over it with you again. Thanks for watching.